I'll hand it over to you. Okay, great. So the recording is on. So everybody, well, through our sort of pre-talk banter, you might have already heard a little bit about Courtney, you know, that she was doing her PhD at University of Washington and, you know, grew up in Tacoma, or at least her parents are still there. So, but more of the official bio is that she's a professor, an assistant professor at McGill. And she works a lot on optimization as it pertains to machine learning. And so it looks like from her talk, she's going to tell us more about optimization today. A few notable recent things she's done in her past. She was visiting Google Brain in Montreal for a while, and that's where I met her because I was just sort of on my way out as she was coming in. And then she was at University of Waterloo as a postdoc before that, and she's also done a postdoc at Lehigh University prior to Waterloo. So we are delighted to host her virtually at Vector. For the students in the audience, we do have a student roundtable from 4:15 to 4:45. And you're welcome to join. Erin will share the details with you, but we should have some time anyways following the talk for a few questions, whether you're going to the roundtable or not. So I will hand it over to Courtney. Welcome as our first official speaker at our Fields Institute collaboration.
Yeah, thank you so much for inviting me here today. I'm excited, and hopefully I could one day visit again Fields. I've been there once a long time ago. Well, now it feels like a long time ago. It wasn't that long. But yeah, so thank you. So today I wanted to talk about some recent research that I've been working on. So I've titled it SGD in the large, but it's not just SGD. I hit the wrong button. Oops, I gotta get used to all this. I just wanted to give a shout out to my collaborators. They're amazing. I've been working with them on this group of research. So this Fabian and Bart, who are both at Google Brain in Montreal, graduate student Q1, who's at McGill now, and then my husband Elliot, who's actually a random matrix theory person. So it's gonna be related to some random matrix theory in here. Who we started this collaboration due to the pandemic because we were stuck together in an apartment. So I want to start off with what we tend to solve for optimization problems in machine learning. So we tend to look at minimizing large sums of f sub I. And the goal of our optimization, right, is we want to, find the number of iterations until we reach some sort of epsilon suboptimality. So we want to know when is the gradient less than epsilon, or when is the function value less than epsilon, or the distance to optimality. But in the world of sort of machine learning nowadays, there's another aspect about these functions, and this is the idea that often we're working in the high dimensional regime. And what this means for us is that it's a large number of samples, so the N is large, but also a large number of features, so the D, the space that you're minimizing. And you can think of this in terms of, say, neural networks, where you have lots and lots of samples and it's large, but you also have lots and lots of parameters or features. Okay, so we're working in this regime where both features and sample size is large. And oops, sorry, I keep hitting the wrong button. The traditional way that we analyze algorithms is through this idea of worst case complexity. So here what we do is we put very general assumptions on our functions that we're minimizing. And we say, well, given any of those, anything from that class of functions, how many iterations does it take for the algorithm to reach some sort of suboptimality? How many iterations does it take to be within epsilon of the distance to optimality? And what's great about this is that you can guarantee convergence. So when you put a general statement on your class, you can just always guarantee that your algorithm is going to converge by doing this type of worst case complexity. And the types of assumptions that we generally make about our functions are very general, like smoothness and convexity. Now, a downside of worst case is that it doesn't really capture high dimensionality. And what I mean by this is this idea that these bounds that we use to create our complexity result don't care if you're working in dimension 10 or dimension 1,000,000. It doesn't matter what dimension. right? It's still a bound based on convexity. And so it doesn't utilize this high dimensional structure. So here's an example of a picture of this. You can imagine, here's your iteration. So the iteration of an algorithm, you're running your algorithm many, many times and measuring the suboptimality, say function distance to optimality or function values. And in the worst case, because you're putting, you can put any type of function on there, you're going to get something much higher than what you actually see in practice. A lot of the runs are not necessarily near this worst case complexity value. So what makes high dimensions so different compared to low dimensions? That was sort of the question you might ask. And the main thing to think about is that when you're in high dimensions, you have more room. And so there's more possibilities for the inputs into your algorithm. And in particular, the input which generates sort of the worst case complexity can be very, very far from typical because you have a lot of them. And so the idea in high dimensions is that if you want to capture this high dimensional structure, you need to put more assumptions. More assumptions will give you better complexity results, but these assumptions could only really be seen in high dimensions. So you're not going to see them as a low dimensional structure. For example, the thing that we're going to be utilizing in this talk quite a bit is something called delocalization of the eigenvectors of your data matrix, meaning that your eigenvectors of your correlation matrix don't line up with the axes. So you can imagine in high dimensions, you don't often end up with an eigenvector which looks like a 1, 0, 0, 0, 0. It's generally not one of those, okay? You have to get very unlucky if you had that. So this naturally kind of leads to how do you add more assumptions in high dimensions? And one way of doing this is to put a probability distribution on your inputs. And this naturally leads to the notion of average case complexity. So here, average case means that you're going to compute the complexity while averaged over all of the possible inputs. Put this distribution on, you average it out. And it tends to be more representative of typical behavior of an algorithm. And so the classic example of this is the simplex method, which we know in its worst case is exponential in the number of constraints, but in its average cases is polynomial. So most problems, it'll run really fast. And that's kind of what you see in this left picture here, is that in the bottom, it's like the input space into your algorithm, the possible things you could add. And the z-axis is the runtime of the algorithm. And what you would like to capture for complexity theory is you would like to actually capture a lot of the times the average behavior, so the thing below. And the worst case behavior is just every once in a while, there's sort of an input which causes a huge spike, for instance, in the runtime. Okay, here's another example of it on the right as well. And what's great about these is sometimes they lead to better algorithms if you look at average case complexity versus worst case complexity, but we rarely use this in optimization. And I'll explain some of the challenges about that. I just want to talk a little bit about some prior work in this area. It's mostly done, average case ideas have mostly been done in the numerical analysis regimes for computing complexity of algorithms. Some notable ones, as I mentioned before, were the simplex method. Quicksort is an example of it, which is an algorithm which is pretty efficient, and that's one way of seeing why average case gives you better algorithms. People have been looking at this in the optimization much more recently through conjugate gradient, and people have seen sort of some empirical evidence using some of these average case complexities that average case is really what we want to capture in these optimization algorithms, but hasn't been explored a lot. Gosh, I keep hitting the wrong button. Sorry about this. So I would say that there's kind of two critical critiques of average case complexity that you'll hear a lot when people compare with worst case. And the first is you have to sort of define what you mean by a typical convex problem or typical strongly convex problem. Like, what does typical mean in this case? And the second thing about it is once you've defined even a typical problem, you also have to put the correct sort of probability distribution on it. And the question is, how does that probability distribution affect your complexity? So what is kind of believed is that, you know, the complexity theory, the complexity of your algorithm really depends on that probability distribution. If you change the probability distribution, you would get a different complexity result. And as a result of that, it's not a great way of measuring, because, you know, you have to do it for every different type of probability distribution that you put on here. So I'm going to look at the very first problem. I'm going to tackle that one first. And the way we're going to look at this is through sort of a high dimensional and putting an idea of a random matrix theory on our data. So what's the easiest convex problem that you can think about? For me, that would be the quadratic. I hope that's true for a lot of people. So we decided to start with the easiest problem to tackle this typical convex, which is just look at least squares. Here we're just trying to minimize ax minus b norm squared. And now it becomes clear, what do you mean by inputs into the algorithm? So the input into your algorithm would be, say, like a data matrix A here, and a vector, outputs or targets B vector. So those are your inputs. Okay. And so what we're thinking about in terms of randomness is we're thinking of making our data A matrix random and our vector, our targets, also random. And what you see is something kind of surprising. So let's suppose we generate a random matrix A and we generate a random vector B and we run SGD on this. Okay. And what I've done here on the left is I've computed, I've run SGD for 10 times and just computed the quantile of those 10 runs. And on the left-hand side, the y-axis is the function values, and on the x-axis is the epoch, number of iterations for SGD. Okay, so here I'm just setting n to be equal to 64, so I have n samples pretty small, but as you increase n, you make the dimension of this matrix much, much bigger. What you see is, you can see here 10, 20, 24, that the variance between the runs is actually decreasing. And as you get down to like 10 to 496, there's almost very little variance in the runs of SGD. And this is actually an idea that SGD is actually concentrated. So what's happening, surprisingly, is that for large models, so as you make your dimension bigger and bigger and bigger, so you make the number of samples and features larger and larger and larger, the actual path that SGD takes is actually going to a deterministic function. So SGD stops becoming random in high dimensions. It actually just converges to this deterministic smooth function, and you can analyze this smooth function. And that's the cool thing about it, to say things about step size, to say things about convergence behavior, etc., can all be analyzed by just looking at that deterministic function for SGD. So I need to make one point here, which is that I'm not just increasing arbitrarily the dimension or the number of samples of my matrix. I'm doing it in a controlled way, in the sense that I'm making sure that the ratio of the number of features divided by the number of samples is fixed. So as I increase n, I'm also increasing the number of features. Okay, so that's kind of the model behavior that I'm looking at. But it's still cool that you get this concentration. So now you may be saying, okay, that's great. You told me I just choose a random A, random B. What do you mean by random? And this goes to the second point of, well, maybe my complexity result really depends on this probability distribution of my inputs. And the idea that we're going to use here is that if we model these things as random matrices in high dimensions, there's a notion of something called universality. This is an idea from random matrix theory that I'll talk about in a moment. But it helps us with this idea of how much does the complexity depend on the probability distribution. So the idea here is, what distribution should we make for our data, our outputs, and our initialization? You can think that that's also an input into the algorithm. So the framework that we were looking at is we were looking at a generative model. So here I'm thinking of my targets as being equal to A times some signal X tilde plus some noise. Okay. So I'm looking at a random matrix A. I'm going to normalize it. My targets are going to come from a signal plus noise, where my signal is random. It doesn't have to be initialization. I'm going to also make random. Again, those actually don't matter so much. And then I'm going to add some noise to it. And again, the key thing here we're always going to be thinking of, we're always going to be thinking of high dimensional regimes where the number of features divided by number of samples is converting to some fixed quantity. So the ratio is always some fixed number. Okay. And the other important assumption is because I'm changing dimensions, I'm going to, I'm making things bigger dimension-wise. I'm always going to have to sort of normalize things correctly so that things don't just go off to infinity just because I'm making dimension larger. And one of the things I'm going to normalize is the signal to noise ratio. So I'm going to always make it so that as I increase dimension, my signal to the noise is constant across dimensions. So it's not like I'm decreasing the noise as I get larger, and increasing the signal is constant. Okay. So you might say, okay, again, you haven't really told me what my data matrices are. What do I mean? So here's sort of the assumption that I'm going to make. It's not really on the matrix A so much. What's going to be important here is actually the Hessian. So it's the A transpose A, or the sample covariance. You could even think of the data. And here's how this question of dependence on the probability distribution for complexity is kind of interesting for us in high dimensions. It's that in random matrix theory, so many classes of random matrices sort of share characteristics with each other. They don't depend on the distribution of the entries of this random matrix. They only depend very mildly on low moments of their entries. So it doesn't matter if you generated your matrix using a Gaussian or you generated your matrix using Bernoulli or any other distribution. Most random matrices in high dimensions kind of have the same properties. They share some properties with each other. And one of those properties is this delocalization of the eigenvectors of this H, meaning that the eigenvectors are not aligned with the unit vectors. So if you generate a Gaussian or you generate a Bernoulli with entries being Bernoulli, it doesn't matter on the distribution. They all have in high dimensions eigenvectors which are kind of not aligned with the unit vector. And the classic example of this is if you generated a matrix, the entries of a matrix, Aij, which are normal 0, 1, then it's quite known that the eigenvectors of A transpose A of the Hessian are uniform on the sphere. So that's the most general example of that, but it's true for a lot of other distributions of entries of data. So what are the actual assumptions I'm going to put onto my Hessian, my least squares, my data? Well, again, I'm going to assume that the model size divided by the number of samples is fixed. Okay, as I increase dimension, I always have to do that. The other thing I have to do, and I think this can be removed, it's an open problem to do this, is that I'm going to have to assume that I have an orthogonal invariance on the left side of my matrix, so that if I take an orthogonal matrix and I hit my random matrix, it's in law the same as my original matrix distribution. This is really kind of an assumption which just says that the samples are independent of each other. That's basically what this orthogonal one says. And then I need a mild assumption on the largest eigenvalue of H being bounded in independent event. So the max eigenvalue doesn't go off to infinity, and it converges to some finite thing. So what are examples of data distributions? Well, as I said before, you can take the entries of your A to be just normally distributed. So that's an isotropic type feature. You can take sample covariance matrices. So you can take normally a Gaussian matrix and multiply it by any positive semi-definite matrix to get some sort of covariance structure between your features. That works. That also satisfies this. A fun one to think about is bounded norm matrices. So you can assume, you can look at all matrices which have eigenvalues, or they're A transpose A, the eigenvalues of A transpose A between two fixed quantities, little l and capital L. And you can put sort of the uniform measure on that. That satisfies all these properties. Oh, and the last one you can think of is you can do linear neural networks. So if you think about multiplied a product of Gaussian matrices and just training on sort of the last layer, the product of those random matrices together, as long as they're Gaussian, will satisfy these assumptions on my data matrix. So it's a pretty interesting class. Okay, so you might say, go back to the problem and say, okay, you said that SGD concentrates and that it didn't really depend so much on my random matrix. It seems like a lot of these things depend on what does this limiting loss, this function that SGD converges to, what does it actually depend on? If it doesn't depend on the distribution, what does it depend on? And the answer to that question is it depends on the spectrum of the Hessian, and only the spectrum of the Hessian in that case. And so just to give you a picture that the spectrum also has some nice properties, you can look at things like isotropic features. So these are entries of A, which are IID. They have mean zero, the same variance. That's sort of a low moment assumption, and finite fourth moment. And if you compute the eigenvalues of A transpose A, you actually will see that they converge to a deterministic distribution. And that distribution is the Marchenko-Pasteur. So that's kind of cool. So like, again, eigenvalues also kind of don't have this so much of a dependence on the distribution. The way you can think of this, if you're lost in the random matrix theory, is this is like the central limit theorem and law of large numbers for random matrices. If you think about the law of large numbers, it says if you take sums, it doesn't really depend so much on the distribution, just on the mean and the variance, that they'll converge to the same quantity at some normal distribution. That's what's happening here, but to the eigenvalues, and that distribution is not the normal one, but something called the Marchenko-Pasteur. Kind of cool. So in this sense, you can think of also this model, this isotropic model, as random white noise. This would be if you had just pure randomness in your data, the eigenvalues would have this shape. It would look like Marchenko-Pasteur. So it's kind of cool. Okay. What's also interesting is that you can, I've said that this loss function somehow seems to only depend on the spectrum. You can take real data like MNIST, compute its spectrum, and see how well you predict the behavior of SGD. And we did that here. So we took the spectrum and this, and we ran it. We ran our prediction, which only requires the spectrum, with this guy, and we saw how it compared with actual SGD on MNIST, and you get a pretty good match. So you can predict the behavior of SGD just from the spectrum. So that's kind of a cool thing. And so you might be saying, how do you actually go about showing all this? So I'm about to show you what this deterministic function looks like. So to begin with, I want to just point out that what SGD I'm actually looking at. So I'm looking here at minimizing a least squares problem. So here my FIs are kind of like AIX minus BI squared. Okay, and I'm running SGD with a fixed step size gamma. Okay, so gamma is fixed. What I'm going to be talking about is last iterate convergence. Okay, and I'm going to be doing this where I'm allowed to repeat data points. So I am doing multiple passes over the data set. This is not the streaming model. This is where I actually can reuse the data over and over again. The other thing to note here, this is a small batch study. There's you can extend this to larger batches, but it's a little bit tricky. And then just to point out, what is the worst case for SGD in this? Well, you get something which looks like the expected function value. So here, this expectation is just taken over SGD, the algorithm itself, how you update your gradient, your stochastic gradient, not over the data. And what you get is that you get an exponential rate, which somehow depends on the minimum eigenvalue and the largest eigenvalue of your Hessian, plus something which is like a neighborhood. That's sort of the worst case SGD. And in my setting here, I'm going to always let T be the number of passes through the data. So T is always number of passes. So what can you prove? So you can show this really cool theorem. This is the concentration of SGD, that as you make this dimension larger and larger and larger, SGD, the whole path of it will converge to a deterministic function, and you can write down what that function is. What is the assumptions? You just need a step size which is bounded by 1 over the trace. So as long as the step size isn't too large, you can, this statement up here just says that the probability that your true function values f at x and t converges to the predicted function phi or phi here goes to 0. So it concentrates around this phi. And what is this phi sub h function, or psi sub h, sorry, psi sub h function here? It is a solution to something called the convolution type Volterra equation. So the convolution Volterra equation has 2 components. The first component is a component which is what would be present if you had done gradient flow. It's exactly gradient flow. And the second component is actually the thing which makes SGD SGD. So this is the thing which is maybe the most interesting. It's a different, it only appears in SGD. Okay. And if we examine this thing a little bit more carefully, what we see here is that these H's, so you see H1, H0, H2, what I've written down here is what are these H's actually depend on? And these H's are actually sums of these eigenvalues of our Hessian A transpose A. So the lambda I is an eigenvalue of H, of our Hessian. So what this tells you, or what this shows you in some ways, is exactly what SGD will converge to as a function of its eigenvalues, as a function of its spectrum. So you exactly know how does the spectrum change the behavior of SGD. This is well known, sort of in some sense, for deterministic algorithms. I think many of us have taken classes where we've seen exactly that the spectrum is important, how the spectrum looks, how does it affect the algorithm, like CG. Here's the same exact thing, exact expression for SGD. Okay. Another way to think about this, and if for people who are maybe more familiar with the random matrix theory viewpoint, is you can think of this HK as an integral against the distribution for the eigenvalues of the random matrix. Okay. So what can you do with this? Like, you might be saying, that sounds really cool. Like you found like that SGD converges to a deterministic function. But what can you say about it? Like, is there anything interesting, anything neat you can say? Well, one thing you can say is stuff about step size. And this is sort of surprising. So here what I'm plotting on the right is the convergence rate of SGD as a function of its step size. And what you see here, which is very different from gradient descent, is that there is a critical step size. And what this means is that when you're smaller, your step size is smaller than this critical value, then your convergence rate depends on your step size, is kind of linear. It looks like you just, your step size just is like gamma times the lambda mid. That's the behavior, how it affects it. It's what you expect if you did gradient descent type behavior. But there's this point where if you go above this critical step size, the convergence behavior of SGD changes, and it's non-smooth. So the function is a non-smooth function. And what you see is above it, you get a little bit faster, but now the rate is not a linear function of the step size. It's actually a non-linear function of the step size. So it's a very different behavior on that other side. This kind of explains why people take very large step sizes in SGD. This is one of the reasons. You actually get a little bit faster by taking something larger than what you expected to be able to. And it has a little bit to do with the fact that there exists this critical step size in SGD. And you get this all by analyzing that convolution behavior. And you can see that the optimal step size is always just a little bit above this critical one. So you can see here, there's these sort of quadratic-y looking things. So the optimal one would be where the minimum of that quadratic is. But as you see, as I make R, so that's my ratio of number of features to samples, go to 1, it converges, the optimal converges to the critical one. So the critical one is kind of an important quantity in here. But this is something of a cool and thing that you can get just from knowing that. So I started this talk by saying that I was interested in average case complexity. So I want to say, how do you actually get average case complexity from all of this? So I'm going to do this in the isotropic feature study. And what's interesting, did it work? There it goes. Oh, one button. Oh no, I skipped a slide. There it goes. Isotropic feature is that we need to understand the distribution for the eigenvalues of our Hessian. And so if we look at this Marchenko-Pasteur, we see some kind of interesting behaviors occurring. So one of them is that if you look at the model size D over N, number of samples R, when R is bounded away from 1, okay, meaning that you have sort of either more features and samples or more samples and more features and samples or less features and samples, other way around. Either way, what you get is a gap between the 0 and the next non-zero eigenvalue. So there's actually sort of this gap that appears when R is not equal to 1. Now, when the model size and the number of samples are equal to each other, or proportionate to each other, so they're 1, this gap disappears in the spectrum. And so you have eigenvalues in very high dimensions, eigenvalues which are really, really close to 0. Okay, you don't see this in finite dimensions. So in finite dimensions, you always will have a gap because it's a finite dimensional matrix and you're computing a positive definite matrix from it. But in high dimensions, as you make it larger and larger and larger, you see eigenvalues which are really, really close to 0. And what this means is essentially that you should expect different behaviors depending on this value of R, this ratio. So when R is not equal to 1, because you have a gap, you expect a linear rate of convergence because it's behaving more like a strongly convex function where you actually have a gap in high dimensions. When R is equal to 1, you should expect something which is more like a convex function because you have eigenvalues which are really, really close to 0, that you're basically behaving like convex. So we expect different convergence behaviors when R is equal to 1 and when R is not equal to 1. This idea, this use of R is also used a lot in generalization. It's that double descent type curve behavior that you see, that when you have sort of a proportional model size to samples, R is equal to 1, you have generalization error goes way up. And when you're away from it, it goes way down. So this R is kind of modeling how many either over or under parameterized, or when you kind of are at the critical point of over and under parameterized. But it has effects on the convergence behavior also. Okay, so how do you actually do the average case? So what do? Well, you have this notion of your spectrum. So all you have to do now is plug in for those eigenvalues, that distribution for your eigenvalues into the HK. So you generate your eigenvalues from this distribution, and you can just plug them directly into this sum, and that will give you what HK is. So now you have those. And then if you want to find the average case complexity, well, you can say, well, you know, my true function, the thing where I'm running SGD is basically psi. It's exactly psi. So at that point, you might as well use psi to measure your optimality condition because you're in high dimensions and they're exactly the same. This is what this high probability concentration result says. So instead of saying, well, I'm going to find where my function values are less than epsilon, I'm just going to say, well, I'm going to find where my psi is less than epsilon. And my psi is just a deterministic function of the eigenvalues. And so I can compute that quantity. And that's all you have to do for the average case. So this is a way to use the fact that you don't need to actually look at your true function values. You just have to look at this predicted one because you know in high dimensions they're indistinguishable. And you can do that and you can compute the rates. And what you see here is actually that the average case rates under these sort of modeling assumptions in high dimensions actually give you much better complexity rates than what you would have gotten in the worst case for SGD. For instance, in the R is equal to 1, so to the non-strongly convex setting, that convex setting, you get this improvement. In the strongly convex setting, you get even an improvement in the linear rate. The linear rate doesn't depend on the largest eigenvalue. It really only depends on the smallest eigenvalue, which is much bigger, pretty good improvement. And in both cases, so this is where gamma is smaller than this critical and also larger. So you see pretty good improvement from the average case by analyzing the high dimensional setting. I think this is really cool and an interesting way of thinking about it, because in reality, the rates that we got for SGD, I'm guilty of doing this too. Whenever we did a worst case rate, you won't even plot what your predicted rate was, because it doesn't match what actually happens on real data. It's not even comparable. And this is kind of pointing to this argument that we're really, really far off in our worst case rate, is that they're just not matching, especially in SGD. So this kind of begs the question. I think everybody would say, well, can you go faster? Can you beat SGD, right? Like that would be what everyone would hope. And so, of course, we're like, okay, can we do this with momentum, right? You would expect momentum, it beats everything in the deterministic setting. Can we do it in the stochastic setting? And for hopefully many people have tried to prove stuff about stochastic momentum, we find that it gets a little complicated. It's not clear if it's better or worse. So we started to analyze stochastic momentum methods, and here's the class we looked at. So we looked at momentum methods which had a momentum parameter delta, okay? So I'm allowing the momentum to depend on the iteration counter. I adding two different step sizes, so I have a gamma 1 and a gamma 2. This is for reasons, it actually helps to have both of these in here. And what you can show is that for nice momentum parameters, these are things like where momentum parameter is fixed, like some constant independent of k, or for things which momentum parameters kind of depend, like 1 over k kind of behavior, like a Nesterov type behavior, that all those have a similar concentration result like SGD, and they concentrate to the same type of equation, which is a convolution type Volterra equation. Now, it's a different convolution type. It has different S and different kernels, not exactly the same H. It's not as nice to write down, but it has the same convolution type structure. And as a result of that, you can actually analyze these methods, because convolution type Volterras are easy to analyze relatively. They have a theory behind them. And you can get expressions for it. So you can analyze average case, step size, momentum selection, all of that, because you have this deterministic equation that it constitutes to. Now, we didn't actually show that the concentration. We have a heuristic argument to show that it mimics the true dynamics. But it's an open problem in reality to actually show this concentration. And it's really we're in a matrix theory problem. So if people are interested, there's a nice little problem to try and prove, to actually show prove the concentration result like the SGD. But just to convince you that this actually works, you can plot similar things to SGD, where you run these different momentum methods. So I'm running sort of a stochastic heavy ball, and then I'm running one which is kind of like a Nesterov. So it has a momentum which is like 1 over k. And what's cool about, and you can plot what we predict, but what's kind of cool about this is that just like you expect in momentum methods, you kind of expect the function values to kind of go up and down. You actually can predict the movement of the momentum methods going up and down, even in the stochastic setting. So you can kind of see that in the upper left picture. You can see it goes up and down, and the red line is the prediction of it. And so, like I said before, if you have this prediction, just like in SGD, you can analyze average, you can analyze parameter selection from it. And so I'll go into a little bit more detail in a second about some interesting results about the parameter stuff. So I'm going to focus on two different of the momentums in particular. And the first one is just sort of like a stochastic heavy ball, which is that I'm going to make my momentum parameter just fixed, independent of n and d. It's just some theta. Okay, some value. Okay, And we know in full batch gradient that things like this, there's a choice of theta and gamma for which heavy ball will guarantee you a faster convergence than SGD or than gradient descent. And the question is, well, what about something like stochastic heavy ball? And what you see is a slightly sad picture. At first, it doesn't look this sad, but if you stare at it long enough, you'll realize. But it turns out that, in fact, you have no gain in stochastic heavy ball from SGD. That the gain that you are seeing sometimes from running stochastic heavy ball is actually the result of choosing a larger step size in SGD. So there's actually, you can show a correspondence because you know SGD is converging to some deterministic function. Heavy balls also could determine to some deterministic function. You can just compare those two deterministic functions. You can actually show that the two deterministic functions are identical under a transformation of the step sizes. So this kind of, it's sad because everyone's always like, oh, momentum is the greatest thing in the world. It works so well. It's what we use a lot. But a lot of times it might just be that you're just choosing a larger step size for SGD and that's really the benefit that you're seeing here. Now, I say this all with one caveat. And the one caveat was that, and this is what this picture is showing. So here I'm showing the last iterate function value. So I'm looking at a function value at a fixed iterate, and that I'm varying theta and gamma so that this ratio of gamma to gamma over theta is equivalent in SGD. And the red and the orange lines are the deterministic ones, respectively, for SGD and heavy ball. And you can see that they match. But there's one spot where you do get a difference, and that's precisely when theta, your momentum parameter, starts to depend on dimension. So I made one assumption at the beginning when I was looking at this, which was that I didn't want my momentum parameter to depend on dimension. And if I don't make it depend on dimension, it seems like it degenerates back into SGD. But if it depends on dimension, there's just a tiny, tiny improvement. And I don't think I can zoom in small enough, but you could actually, if you zoomed in on this plot, you would actually see that the red curve will dip below the orange curve. Basically, when your theta, your dimension parameter is n dependent, it's dimension dependent. And so that is sort of the reason why you might say, okay, you know, if you have momentum parameters which don't depend on dimension, you just kind of degenerate into SGD. So maybe you can do better. How do you do better? Well, you're going to have to make your momentum parameter depend on samples, on dimensions. You can't just choose a momentum parameter that works for every data set. That's not true. It's going to have to depend somehow on a dimension. And that's what you can do. So that's what we did, and we made it depend on dimension, and that's what we're basically calling Nesterov. You can imagine that if you make your momentum parameter depend on the iteration count, you're essentially making it depend on dimension, because eventually it will be over dimension. The iteration will beat the dimension. And so that's what we're doing here. So we're adding a dimension dependent constant for our momentum. And I'm going to take two different step sizes. This is actually important. It doesn't quite work if you only take one, and can't really explain to you why it doesn't work with just one, but you really do need two. Okay, and so this is, ethane is kind of the idea of adding a dimension dependent momentum parameter. And when you do that, you actually get faster convergence, especially in the case when R is equal to 1. You can beat SGD with this, and beat it by a lot. You go from a t to the -1 convergence rate to a t to the -3. And this is by making the dimension kind of depend on, making the momentum parameter depend on dimension. So that's kind of a cool thing here. So this is a plot of varying R and running both these algorithms, and you can see that there's a peak. You get really fast, much better convergence. The purple being the better one, the dimension dependent. momentum parameter when R is equal to 1, and then it gets kind of muted out as you go away from R is equal to 1. It starts to behave more like SGD again. That's pretty cool. Just to point out that all of this still applies to real world data sets that you can predict. You can again run things like spectrums, MNIST, and use it to predict the behavior of momentum algorithms, stochastic momentum algorithms. Again, they only depend on the spectrum, just like SGD somehow only depends. So I think that's really cool. I think there's a lot to be done here. So I just wanted to end with sort of what I've kind of shown you, which is that I'm kind of giving you a framework for analyzing concentration of sort of stochastic algorithms using the sort of random matrix theory idea and looking at high dimensions. And I think it's really cool. There's lots of open problems in this area. We got to see the dynamics of stochastic algorithms. We were actually able to write down formulas for the dynamics, and you can actually then predict the behaviors of SGD, stochastic momentum methods using this Volterra equation. And then you can analyze this dynamic to get things like step size selection, momentum parameters, average case analysis, all sorts of that. And there's a lot of open questions with this. This is kind of, and I would say, a different way of analyzing algorithms that we haven't been doing, using these random matrices, data, trying to get exact predictions. So some very like everything's open in some ways. So one of them is like, can you extend this beyond least squares? What would be the natural assumptions? How do you model your data in that case, or your inputs in that case? What are the true probability distribution assumptions? So I kind of talked about this delocalization. That's probably one. Is there even more general than that? That would be nice to know. And then I mentioned that we didn't actually prove the concentration result for momentum. So if you're looking for a problem, that's a good problem to prove the concentration for momentum. There's a nice random matrix here. It's pretty well thought about. And so I want to say again, thank you for inviting me here today, and to just say that this work is based off of 3 papers, all of which got accepted recently. So that was kind of nice, nice surprise in the last couple of months. Yeah, so it's based off of a Cole paper, a paper which will appear in NeurIPS, and one which is in the Foundation Computational Math. So thank you again for inviting me, and yeah, thank you.
Thank you, Courtney, and congrats. So you don't always see all the work get accepted, but it looks like it all worked out really well this time. So fantastic. Right. So my mind is sufficiently blown. I definitely got my math lesson today. So let's. I see some virtual applause. We can take questions. We reserved right up till 4:15, so we got lots of time. We can turn it over to the floor. Please feel free to put questions in the chat, or you can put your hand up. I might get started because I don't see hands up right now, just to break the ice. So I was wondering, Courtney, like you showed this MNIST analysis, which is a classification problem. And I was kind of trying to resolve the least squares kind of regression setup to the classifier, but maybe it doesn't really matter because you're just looking at the Hessian. So maybe you could talk through that a bit and, how to resolve this sort of least squares versus classification issue.
It's a very good question. So we here just pretended that MNIST was a regression problem and used it like a regression type issue. But it's a good question of doing this for, say, a logistic regression, of running this algorithm. We've done it. Logistic regression seems to also have this concentration, but it goes into this question of how do you extend beyond least squares? And it's a great problem. Like, how do you actually prove that that even the classic or logistic type regression problems concentrate and have all the same nice properties and you could analyze as well. So that's actually an open question in some ways. But I didn't put the picture up here, but there is one for logistic, which shows that it concentrates as well. So that's pretty cool. It seems to suggest that there's more to this theory, high dimensional. So yeah.
All right. All right. So who's got questions?
Did I confuse everyone with my math? I'm sorry. I'm a math person.
No, there's some mathy people in the audience. I can recognize them. There's some people that like limits out there for sure. So don't worry. I'm sure they've got some questions too. I mean, I have a couple more. So until people might be a bit shy. So one other question, Courtney, is you at the very beginning of your talk, you're saying how average case analysis may drive better algorithms, and maybe you could talk a bit about, it looks like, well, you have the algorithm to do the analysis. So how does the average case analysis feed back into the algorithm design? I guess you're showing kind of at the end that you had developed novel variants of as sort of momentum SGD. Is that kind of the process here? You start with an algorithm, analyze it, and then use that to drive the development?
I mean, so this is the way that this algorithm came about, but there's also other ways. One way is, if I can go back maybe a little bit, another way of doing this is you can imagine that you sort of know that it's going to be some sort of convolution type behavior driving it. And if you fix sort of the spectrum, you can start to argue, well, what's a good choice of a I kernel matrix? So if you know the kernel and you know the F, you can then create the algorithm from that. So that's another way of doing it, is fix this. Well, what's the best F and I could choose so that I actually produce the smallest complexity, or the best sort of convergence behavior for this function. It's a little bit hard to see in this picture. It's a little bit easier in deterministic ones, where because you don't have convolution type stuff, but you can actually choose, in some sense, choose what F and I can be, and that actually picks out the algorithm for you in some ways. So that's what I also mean by a way of deriving average case algorithms. It also leads to what might be optimal average case algorithms. if you want to say that, like you fix the spectrum behavior, what kind of spectrum you expect to see, and you can derive sort of the best F and I for that fixed spectrum, and that would create your optimal average case. And I think maybe that's what's surprising, maybe not surprising, but if you look for deterministic algorithms and you do this, so you assume everything is deterministic, you don't have stochastic, but you still put in random A's and random B's. Polyak, Momentum, Nesterov, they're the optimal ones for specific distributions of your spectrum. If you assume your spectrum has a certain way, they're actually the optimal average case, or nearly optimal average case in many cases. So that's, I don't know if they derived it that way. I don't think they did, but they also will get the optimal there. It's not clear what the right one for stochastic is, though. So again, that's kind of more open.
Okay. Lots of open questions or open problems.
Sorry, yeah.
Hand up. Mihai, go ahead.
Hey, can you guys hear me?
Yeah.
Yeah, so I guess the one thing that I wasn't quite sure on, like you had a nice equation for F, which I guess is the amount of error, like the L2 error. Mm-hmm. Is there a statement about what the convergence of the actual parameters converge to? Like, is it the same as in the non-SGD case, like just a gradient flow case, or is it converging to like a different solution? Because in this overparameterized regime, there are many possible solutions, right?
Yeah, it's a good question. So this will converge. So because in the overparameterized, this is a great question. In the overparameterized, if you look at this function, the phi function, your loss is growing to 0. So you know that as time goes to infinity, it has to converge to the same thing as the the gradient flow because the loss is going to 0. So this term, which is making it SGD, is disappearing. So you see here, there's psi and psi on both sides. I hope that is kind of the weird thing here. This term is somehow disappearing, so it's behaving more like gradient flow. Why do I think that maybe I misunderstand your question, but I think this is maybe something that I've also wanted to look into, is that where do you get something different than gradient flow? Like really, where does SGD behave differently? It will be where your loss does not go to 0. So like in ridge regression, then you'll see a different behavior for SGD than gradient flow, because essentially even in ridge regression, this loss term will not go to 0, and it will actually affect even the limiting behavior. It won't just be it won't be gradient flow. It will be a different behavior, really, for those algorithms, for this algorithm.
So is it true that if the error goes to 0, that it must be the same? Like, isn't there a whole manifold of solutions in this over-parameterized regime, and then it could be that like this converges to a different, or like with a different probability to converge to different points in that manifold than the regular thing?
Yeah, it will converge to it'll still converge. You can show it'll converge to the minimal norm solution.
Okay.
It's not clear in this picture, I mean, with this loss, but the sort of reasoning is that it ends up depending on psi. I say this all and then say, with ridge regression, it won't do that. It will not have the same, it will be a different you can show it doesn't converge to the same value as SGD or as gradient flow does. It's like something different. And the reason is that in the end is that provided that your loss is not going to 0, it just doesn't behave like gradient flow. So it seems like for all these algorithms and how the iterates update, there's always a term which looks like gradient flow plus something which hurts you. This goes against what we believe of SGD, but you have something which is gradient flow plus something which is always worse than gradient flow. And that's what the second term is. It's worse than gradient flow. It's positive. It's everything. So it's in some sense worse. But it's this term which it always involves something with the loss. And if the loss is not going to 0, it has it'll converge to some different behavior. Everything will be different about it. That's kind of how you should view it as. It leads to interesting questions about generalization. It seems to suggest for the linear case, for this least squares type problems in the setup, that SGD is actually worse than gradient flow. If in the sense of the following, if you had infinite computational time, so you were allowed to run forever and ever and ever, eventually there would be gradient flow would beat your generalization behavior for SGD. That's what this suggests. If you take into account computational time, because of these things like, I mean, you see the step size here can be taken to be much, much larger in SGD. If you take it into account the computational time, SGD is better. But it's only a computational time. It's not if you had infinite computational, SGD seems to be somehow worse than gradient flow. I find this kind of against what people believe. I don't know.
Okay, I guess this is really great. The follow-up, I guess, is, do you think that the theory is close to like real life? Like this is all on this limit where R is fixed or whatever. Like, do you think that that's a realistic
behavior?
capturing of what's going on?
It's a good question. I think for convex problems, this is probably true. This behavior is probably pretty good. Unfortunately, I don't think it matches it, and it shouldn't match the behavior for non-convex. So as soon as you start to really do neural networks, where you have compositional structures and things like that, I think it has different behavior. And I think it would be really cool to do a type of analysis like this that we did for the least squares for a non-convex problem. That's where I think the real difference is. that those non-convex structures, it doesn't have this behavior at all. It doesn't look like this. But I think you can do it. I think it's hard. I think it's really hard, but I think it's a really good problem to look at. It may even tell you things about like that SGD is better generalized than gradient flow in that case, which is probably the truth in the non-convex setting. Even if you had infinite computational time, it's just, this is probably models the linear setting pretty well.
Great,
So,
thanks.
yeah. Cool. Other questions?
Okay. Yeah, I'm just looking at there. I don't see anything else in chat, nor do I see hands up. Mihai's hand. Mihai, that doesn't mean you have another question, right?
Oh, I can make up another one. Yeah, sorry. This is
No,
You
you don't have to.
I mean, I was just skimming through the papers. Is it true that is everything proven for the expected value, or is it like an almost sure, like
It's
for
an
the
almost-
actual?
Yeah, it's an almost sure. So it's with
Okay.
high probability type. It's an actual concentration. The expectation, we proved it doing like a moment calculation. That's why it has all the mean expectations and variance computations in it.
Oh, okay, so then it's like a polynomial concentration then, rather than a exponential one if you did it all with moments, or maybe not.
You can get, so this is it's exponential. I mean, it's exactly what this theorem says. So it has a p to the minus epsilon behavior. Yeah.
Okay, got it. Okay.
Yeah. But it's a concentration. It might not even be phrased in this format. We may have only said in high probability in some of the papers because we got lazy. But yeah, no, it's a concentration result. So not just expectation or variance.
Great.
Yeah.
Okay, thanks. Yeah, now I'm really out of questions.
Are you interested in doing this? Are you wanting to do some?
Yeah, this is kind of close to my area, so I think it's pretty interesting.
Cool. Do you do random matrix theory or?
Yeah, so actually my like PhD thesis was like really hardcore random matrix theory, and then I sort of moved to doing like things that are applied to machine learning, and so there's always like a little bit of random matrix flavor, but not as much as this, I think.
Yeah, there's some really nice questions in random matrix theory which are kind of related. That you really need random matrix theorists, and they don't fit in the classic random matrix models. So like I think Graham was talking about classification. Classification cannot really be written in, I guess, as like a IID normal times by a covariance. It doesn't seem to fit that model. It needs a different model because you would think of it as two classes and each class has a covariance structure. So there's some weird there's like, it's not exactly that form. So like analyzing the behavior, like that's a main block sort of for logistic regression, is just what is the random matrix model, and what can you say about that random matrix model? Like what are the eigenvalues of something which has classes which have two covariant structures? What are the eigenvectors? What are the eigenvalues? That kind of stuff.
Right, yeah. The other thing that popped into my head was there's this stuff by Pennington where he has like sort of the large limit, and it's also very Marchenko-Pasteur. And so I wonder if you could like gel this with that and get some kind of a SGD limit for that model.
Yeah, no, I'm actually been talking with Jeffrey because he's at Google Brain, and so he brought this up. He was like, yeah, he was exactly asking this. Yeah, for like a random features model, because he did a lot in that area, and just a gradient flow. And he's been asking, oh, can you say anything about it for SGD since you have everything? I think you can. I think it's possible. That this is basically the right behavior for SGD from the random matrix theory viewpoint, and you might be able to do random features. It's a little bit tricky with random features, but it is possible. So Cool. I didn't know you were interested. You knew Jeffrey's work too.
Yeah. I met Jeffrey at some like random matrix type conference a few years ago. So, and
Yeah.
we've talked a few times about stuff like this. But yeah,
Yeah.
I mean, he also has all these like crazy free probability angles on everything, which like could solve like what you were saying a minute ago about having two classes. Like it could be one of these block diagonal constructions where there's one block is doing one thing, when the other block's doing another thing, and you have some sort of insane limit for the mix.
Yeah, no, I definitely think it is. Yeah, there's probably some free probability. You have to. I'm not very good at free probability. It seems really combinatorial. I'm not a great combinatorialist, but I also agree. I think that there's something there with free probability going on.
Yeah, I think well
Yeah,
Jeff would know for sure. He's the expert at applying the stuff to these problems.
I feel like he was even scared of it. He was kind of like, yeah, it's
Okay.
not the easiest. um,
Yeah.
yeah, yeah, no, cool.
It was cool to see Bart moving into this as
Very
well,
well.
because back when I sort of was working alongside Bart, he was working on very different things. So I know this is sort of Fabien's territory, but yeah, not with Bart.
Yeah, Bart was like, yeah, he started getting into it. I think one thing which is really satisfying about this stuff, like the random matrix theory stuff, is that when you have the theory and then you go and run the simulations, like they actually just straight up match, which is like never the case when you do like actual, I mean, when you're doing running on real data with machine learning, like you have this theory, they almost never match. But with random matrix theory, they almost always match. And I don't know, it's very satisfying. I feel like he was very happy, like, okay, you told me to use this step size and I exactly used this step size and it was perfect to what was supposed to happen. I'm like, yes. So I think that's the nicest part about this. I don't know if anyone else feels this way. It's always nice when your theory and your simulations match perfectly. So I think that's what
Totally.
he's got really excited about. Yeah. It's, and also, I mean, there's some numerical issues that you have to be pretty careful with when doing a lot of this stuff. Like you can't actually compute eigenvalues for really large matrices. So to be a little bit careful about the sizes that you're working with. Being a little clever.
What do you use then for computing that? Like some random sort of sampling type thing?
Yeah, so
Or?
this is actually what Bart and Bobby have been getting a lot more into, is trying to figure out how do you compute for the eigenvalues or singular values for really, really large matrices when you have a sample of the matrix. Because you aren't going to actually have the full matrix, you're going to have some sample of it, and you need to compute its eigenvalues. Yeah, so they've been trying to figure it out. There's things which, like there's stochastic CG algorithms which kind of work, but they're a little bit unstable. So things can numerical issues run in. That's why you saw that I only really did like 4,000 by 4,000, because that's about as large as anything can really handle before it starts to really blow up, especially if you're running this a lot of times. If you know, because we know a lot of times the spectrum, and maybe this is another plug for why this knowing the prediction is so nice. If you know that the spectrum is converging to some distribution, you can just use the prediction and use the distribution, which is much easier to work with. Like you don't actually have to compute the whole spectrum. There's that. But yeah, no, it's not easy. And for really, really large models, we actually don't know what the spectrums look like for neural networks. People have been trying to solve this for a while. And they have theory. People think it looks a little bit like Marchenko Pasteur with a heavy tail. A little bit slightly different. But it's a modeling question too. So yeah.
Well, actually, Bart was working on some pretty sort of heavy duty infrastructural type stuff. So I imagine with the resources that you have there and with Bart and those people, like you are sort of maxing out, right? What's possible. So yeah, it sounds like that is sort of one place where it might be limiting right now is in doing those sorts of computations.
Yeah, it is. Yeah. Memory is an issue. It's an actual issue for them. But yeah, it's really cool, and he's gotten into it, and I think he likes it quite a bit now. It's much more numerical.
Yeah.
Do more numerical analysis.
Cool. Well, I
Yeah.
see we're at 4:15. This is the time where we're supposed to be starting the student roundtable. So if there are students still out there, I know a few people are dropping off as we sort of go on and on with our questioning. Please come out to the student roundtable.